Good afternoon. I submitted my first paper on the far zone effects almost 20 years ago. This work was torn apart by an editor, and I was even advised not to carry out any research. Yet I stand here today and feel honored to be the first speaker of the ICCT symposium. Now, let me start with an introduction. You certainly know that integral transformations are a useful mathematical tool for a gravitational field modeling. Perhaps the simplest example is the Poisson integral in the gray box. We integrate the products of the boundary conditions T with the kernel H0 over the entire sphere. However, the boundary conditions may not be available over the full spherical surface, for example, due to distribution policies or impracticality of their collection. We therefore split the sphere into two domains as depicted on the figure, the gray near zone and the blue far zone. The lower box shows only the far zone effect for the Poisson integral. Formulas of this type and their transition to more practical spherical harmonic expansions are the main subjects of this talk. In particular, I will summarize the most valuable lessons from our recent research papers on the far zone effects. In our previous presentations on the topic, we combined various aspects, but today I will concentrate solely on mathematics. Now let's jump directly into the first lesson. It teaches us that the transition from truncated integrals to spherical harmonic series is a four-step procedure. I demonstrate this sentence for simplicity for the far zone effect of the Poisson integral. The starting point is thus the truncated integration from the introduction. In the first step, we introduce the error kernel delta H0 defined in the right box. Its series expansion is composed of multiplications of the truncation error coefficients Q and 0 by the Legendre polynomials P and 0. The error kernel restores the global integration as can be seen from the second expression in the gray box. The second step is trivial. We simply insert the series for the error kernel delta H0. The far zone effect now contains both the global integration and the infinite summation. We next interchange the order of these two mathematical operations. We are permitted to do so by assuming the uniform convergence of the series. Finally, we employ the integral identity defined in the right box. This identity turns the global integral of the boundary conditions T multiplied by the Legendre polynomials P and 0 into the nth degree spherical harmonics of T. As a result, the far zone effect is now represented by the spherical harmonic expansion at the bottom of the gray box. It can be synthesized from a global gravitational field model and a set of truncation error coefficients Q and 0 acting as spectral weights. The four-step procedure is highly transparent because it relies on well-known mathematical elements and operations. The Poisson integral discussed so far is isotropic, but the second lesson considers more complex cases with azimuths. Specifically, it states that anisotropic and non-homogeneous integral kernels must be expressed in orthogonal forms. I illustrate this idea for the far zone effect in the gray box. The quantity on the left-hand side is the horizontal potential derivative Tx. The boundary conditions under the integral sign are the horizontal derivatives Tx and Ty. The integral kernels HA1 and HB1 are functions of the four variables, including the direct and backward azimuths alpha and alpha prime. The geometrical meaning of these azimuths is illustrated in the figure. Now, when converting this far zone effect into its spherical harmonic expansion, we again firstly introduce the error kernels in the right box. These particular equations are based on our earlier research and are referred to as the original form. We can clearly see that the azimuthal and isotropic dependencies are nicely separated from each other. Despite of this symmetry, there is one fundamental issue here, namely the basis functions of the error isotropic kernels delta H star 1 and delta H U1 are not orthogonal. We cannot represent these error isotropic kernels by simple series expansions. I tackled this derivation in 2014 and eventually concluded that a further progress towards a practical far zone effect formula was impossible. I revisited the problem years later during the pandemic. The solution was incredibly easy. I simply used trigonometric identities for alpha and alpha prime and ended up with the new but completely equivalent error kernels in the right box. The isotropic and azimuthal parts are still separated from each other but differently from the previous slide. Most importantly, the basis functions of the new error isotropic kernels delta H plus minus U1 are orthogonal. We can easily find their series expansions and then follow the four-step procedure to get the desired spherical harmonic expansion for this particular far zone effect. But I leave this task for a much longer talk or to you as a homework. Instead, I continue with the third lesson, which is about patterns among mathematical expressions. It says that spherical harmonic expansions of far zone effects keep the same structure for different boundary conditions. I examine this point for the same far zone effect T on the left-hand side of the gray box, but defined by three different truncated integrals after the equality sign. We already know the far zone effect of the Poisson integral on the first line from lesson 1. It originates from the solution of the Dirichlet boundary value problem. The far zone effect on the second line comes from the solution of the horizontal boundary value problem. And by the way, we manipulated with its horizontal derivative Tx in lesson 2. The far zone effect on the third line arises from the analytical solution of the horizontal gradiometric boundary value problem. We can see that the three integrals differ by the boundary conditions and the integral kernels. We can say that the complexity increases with the order of the horizontal derivatives. We apply the four-step procedure and get the spherical harmonic series on the right-hand side. All three expansions include the n-degree spherical harmonic of T, truncation error coefficients Qn, and some other degree-dependent terms. The pattern among the three equations is obvious, and we can encapsulate them by the single expression after the second equality sign on this slide. The different boundary conditions are distinguished by a single index L in here. This beautiful generalization is highly welcome and handy because it significantly simplifies our theoretical investigations and also implementation of the formulas, for example, in a computer program. I now stop with lessons and go to the conclusions. In this talk, I summarized the most important mathematical aspects of the far zone effects for the spherical integral formulas. We have learned that the conversion from truncated integrals to spherical harmonic series takes 4 steps. For anisotropic and non-homogeneous integrals, it is crucial to provide the respective kernels in orthogonal forms. We have also seen that the structure of the far zone effects, in terms of their spherical harmonic expansions, is consistent for various boundary conditions. Overall, we can say that the mathematical understanding of the subject is excellent. I used exactly this knowledge to derive far zone effects for a broad class of spherical integral transformations. The scheme on this slide illustrates the sheer extent of my effort. The far zone effect quantities are located at the upper level and extend from the potential T on the left up to its third order spatial derivatives on the right. The far zone effects can be determined from the 4 boundary conditions located at the lower level. These are the potential on the left up to its third order horizontal derivatives on the right. The scheme also considers arbitrary order vertical derivatives of the boundary conditions that is indicated by the index k in the square brackets. Finally, I would like to advertise our most significant studies on the far zone effects on this slide. These 3 papers describe in detail the mathematical theory, introduce a new and freely available MATLAB software for the calculation of the far zone effects, and discuss numerical experiments on the software validation and even more. So what do you think? Should I have given up on research? Thank you.